Have you ever considered what truly makes an electrical system efficient, beyond just using less energy? It involves a fascinating aspect of alternating current circuits that significantly impacts performance and costs, often silently affecting industrial and commercial operations. The importance of power factor lies in its ability to quantify how effectively electrical power is being utilized by a load. Simply put, power factor is a measure of the efficiency of electrical power delivery, indicating the ratio of useful power to the total power supplied. A high power factor means your electrical system is operating efficiently, while a low power factor signifies poor efficiency, leading to various undesirable consequences. To understand this, we need to differentiate between three types of power in alternating current systems. First, there is real power, measured in watts, which performs the actual work, such as rotating a motor or generating heat. Then we have reactive power, measured in volt-amperes reactive, or VAR, which is necessary to establish and maintain magnetic and electric fields in inductive and capacitive loads, but does no useful work itself. Finally, apparent power, measured in volt-amperes, or VA, is the total power drawn from the source, which is the vector sum of real and reactive power. Power factor is precisely the ratio of real power to apparent power, and it also represents the cosine of the phase angle between the voltage and current waveforms. A perfectly resistive load will have a power factor of 1, indicating that all apparent power is consumed as real power, but inductive loads like motors and transformers draw significant reactive power, causing the current to lag the voltage and resulting in a lower power factor. The direct consequence of a low power factor is that utilities must supply more apparent power than necessary to deliver the required real power. This increased current flow over the power lines leads to higher power losses in the transmission and distribution network, manifests as increased heat, and demands larger conductor sizes and equipment ratings throughout the system. For consumers, this often translates into higher electricity bills, as utilities may impose penalties for poor power factor due to the additional burden placed on their infrastructure. Improving power factor typically involves installing power factor correction equipment, such as capacitor banks, which supply the necessary reactive power locally, thereby reducing the reactive power drawn from the utility grid and bringing the current and voltage waveforms closer in phase. One key detail to appreciate is the concept of kilovolt-ampere reactive, often written as kVAR. This unit is specifically used to measure the reactive power that inductive loads consume and that capacitive loads provide. When you correct the power factor, you are essentially supplying these kVAR locally using capacitors, rather than drawing them from the utility. This not only minimizes your utility's burden but also frees up capacity in your own electrical infrastructure, allowing existing wiring and transformers to support more real power load without needing costly upgrades or experiencing overheating. Engineers often aim for a power factor above 0.95 to optimize system performance and avoid common operational issues. Ultimately, prioritizing a high power factor is about maximizing the efficiency and capacity of your electrical system. It reduces energy waste, minimizes voltage drops, enhances the reliability and lifespan of electrical equipment, and most importantly, it leads to significant cost savings on your electricity bills by avoiding demand charges and power factor penalties. It is a fundamental principle for anyone seeking to operate an effective and economical electrical power system.